Today we're going to be talking about the area of a region between two curves. Okay, so our area of our region between two curves. If you remember the concept of big Y minus little y, you can't go wrong. You take the function that has the larger y values and you subtract from it the function with the smaller y values. And that's going to get you the area in between. So the area here would be the integral from a to b of the big Y minus the little y, all in parentheses, dx. Okay, so our first example. Some of these I'm going to do by hand, and then eventually I just want you to understand the setups. And I'm not going to expect you guys to, some of them I could say, I just plug this in my calculator, okay? And I'll be showing you guys during class some tricks. But the first few, some of them you need to be able to do without a calculator. Because they started adding these types of questions to the AP test where you don't have a calculator, okay? So, area of the shaded region. Okay, so we have the intersection of these two curves. So you have to figure out where x cubed equals x to the third. Hopefully you can see both by the graph and just by knowing some algebra. That's from 0 to 1. So I'm going from 0 to 1 of my big function minus my little function dx. The larger function, the function that I think about it being on top of the other one. The bigger function is the square root of x. The smaller function is y equals x cubed. Okay, so from here, I'm going to do this one without a calculator. X the 1/2. I just like to rewrite that because I like to do lots of writing and make you guys watch long videos. Add 1 to your exponent, 1 over your new exponent. So I have 2/3 minus 1/4 minus 0, still be plugging in those zeros, and here I get 5/12. Okay, so again, some of these you're going to have to know how to do without a calculator. That's why I'm going to show you these first two without a calculator. Okay, find the area region bounded by these two curves and x equals 1 and x equals 3. Okay, so this one always gets me. I don't know why. I won't say it always gets me because it's the first time I'm doing the problem, but y equals x plus 3, I need to visualize this. Y equals x squared. Negative x squared, I apologize, negative x squared. Looks something like that. I'm going from 1 to 3. So I'm trying to find this area. So I take my integral from 1 to 3, 1 to 3 because that's what my function is, the big function, x plus 3, the top function, the function that's above, minus the function that's below, the smaller y values. And also, please do not be forgetting this dx. I'm going to be taking points off if you forget that dx. So here, simplifying this out a little bit. Okay. I was going to tell you guys that even though this is negative, when you're subtracting the negative area, that turns this into a positive. I'm subtracting the negative. So don't worry if the curve goes underneath, okay? So then from here, I'm going to do this one by hand. I may regret this because of the fractions. Well, I plug in 3, so I have 27 over 3 plus a 3 squared, a 9 over 2 plus a 6 minus a 1/3 plus a 1/2 plus a 3. So that all simplifies to, and you can do that math. You can work with fractions. I'm not going to do that in the video because that just makes for a longer video for you to watch. You should get 56 over 3. Okay. Third example. Again, let's get an idea of what these two curves look like. This curve here is a parabola facing up. When I set it equal to 0, I get 0 and 4 as my x-intercepts. I'm going to do this in a different color. I'm going to just underline this guy. I'm going to do this guy in red. So when I graph him, he will be in red. I will do this guy in blue. Setting this guy equal to 0, I factor out my x. I get a negative x plus 6. So his x-intercepts are, or his zeros, are 0 and 6, and he opens down. Okay, actually I don't need that big of a grid. I just really need the first quadrant. 1, 2, 3, 4, 5, 6. 1, 2. I guess I could find the vertex. The vertex, remember, you may not realize this, the vertex happens halfway in between the x-intercepts. So I have 0, I have 4. The vertex is going to happen somewhere for this function, somewhere in between. At 2, you could get that y value. I'm just getting a sketch so I know the big Y versus the little y. This guy opens down because of the negative. 0 and 6, so his vertex happens at 3. So I need to find where these two graphs intersect. So you need to set x squared minus 4x equal to negative x squared plus 6x. If I add the x squared over, subtract the 6x over, I get x equals 0 and 5. So they intersect. Hopefully, as you saw, one was obvious. The other one was at 5 because of my amazing drawing. That's hard to see. So I'm finding the area of this shaded region. So I do the integral from 0 to 5 of your big Y minus your little y with respect to x. The function that was bigger, or the one that was on top, was negative x squared plus 6x. Function that was lower, or on the bottom, was x squared minus 4x. Simplifying that all out and getting an answer, I'm going to do that one. Well, I'm going to steal it from my notes, but do that one in your calculator and you get 125 over 3. Okay, I'm going to skip an example just so that this video isn't super long for you all. And I'm going to jump to this example. Because this example is really, really important. Okay? The functions change. Okay? So from negative 4 to 0, I have one function that's on top, and then that changes at 0 to 4. Okay, so from 0 to negative 4, the red function is on top. So I have x cubed minus x squared minus 14x minus the blue function, which was a negative x squared minus a 2x. Notice how I put those in parentheses so that I can tell the difference, okay? And so that when I distribute that negative through. Now I want to add that to the area here, to the second area. So I'm going to run out of space over here, so I'm going to put it below. I'm not dividing, I'm just putting it below. 0 to 4 now. Now my top function has changed. My top function has adjusted to negative x squared plus 2x minus the bottom function, or the small y's, which are x cubed minus x squared minus 14x dx. Okay, so notice how this changed. It changed because I had one function on top versus another function on top. Okay, so you had to adjust. And I've done this when I've taught this in class. I've done it, and it works out to be a whole lot of fun calculus in there. I would have you guys do that in your calculator, and you get 128 for your answer there. Okay, so that is in terms of x. You can also integrate with respect to y. So like, for example, if when you're drawing lines from one function to the other function, and they're all horizontal lines, okay? Because remember, that's how we started with area. We started with rectangles. So imagine these lines are really thin rectangles, okay? And if one function is always to the right of another, okay? When we're integrating with respect to y, I'm going to make this a little bit bigger. That's a c and that's a d. You're integrating, everything is in terms of y. So you want to actually think about this as big X minus little x. Meaning, okay, the rightmost function minus the leftmost. And everything is in terms of y. I'm going from C to D. My rightmost function is f of y. My leftmost function is g of y. Okay, C and D are y values that bound our area, okay, and these functions here are all in terms of y. And that's why I have a dy there. It's like finding the area to the y-axis. So this one now, okay, find the area between those two curves. Well, those two curves intersect, so if I set them equal, I'm going to get this side to be 0, so I'm going to subtract these 6 over. I can factor out a 6 and a y, so I give a negative 2y squared plus a y plus a y. And hopefully you can see they intersect at 0 and 1. I kind of went through that and then regretted my decision almost immediately. So we're not regretting. We're integrating with respect to y because these functions here are in terms of y. So I'm going from 0 to 1, and there's a 1 there. It might be really hard for you guys to see. I stole this from an old textbook that I used. Okay, so you go rightmost function. The rightmost function is this function here. So 12y squared minus 12y cubed minus 6, I want to do that in the right color, 6y squared minus 6y, okay? And notice how 0 and 1 are all in terms of y. The functions are all in terms of y. That's why I have a dy. When I do that in my calculator, I get the value of 2. Okay, our next example. This one. And I love this example because I love this setup. And it really shows why we integrate with respect to y. Okay, so you could integrate with respect to x, because as I'm drawing my vertical lines, one function's always on top of another one. But here, you change. So you'd have to set up multiple integrals. Okay, so you'd have to set up multiple integrals. You'd have to do something like from 0 to 12 of my x minus x squared over 48 plus dx plus, and then as I go, I would have to go, ooh, that's a fun one, 12 to, it looks like that's at 24. So that's what it would look like in terms of x. But let's integrate with respect to y. So let me erase those. Integrating with respect to y. Notice how when I draw a horizontal line, one function is always to the right of the other one. That's kind of your hint that you want to integrate with respect to y. So we want to do the integral of something minus something else dy. And we're going from 0 to 12, because those are the y values that are bounding our area. And remember, these equations need to all be in terms of y. So my rightmost function is y equals x squared over 48. I need to solve that. I need to get x equals. So I have this function's in red just so that you guys realize what I'm doing there. Okay, and then we have this function here. Well, that function in terms of y is just y. So I would plug that in my calculator. Oh, I don't even have the answer here. Let me pause the video and plug that in my calculator and get an answer for you guys. So I plugged that in my calculator, and just so you know, when you plug it in your calculator, you could use the variable x here. The calculator doesn't know, you're just using the calculator to get the answer, and you get 120 there. Okay, our last example. And this one, I actually got the graph for you guys because I know it's hard for you guys to graph these parabolas. So this is, let me underline it in red, is this function here. And then we have this function here is this function. Okay? And so because when I draw my horizontal lines, one function is always to the right of the other one. Okay? The intersections are -3. So this intersection point is -3. Let's not switch our x's and our y's, Mrs. Marnell. It is 1, -3. And this intersection point here is 5. I keep switching on my x's and my y's because I'm focused on the y. What is that? That is 9, 5. Okay? So, for this one, you couldn't even do this in terms of x because you don't have a y equals for this parabola curve. So that's kind of your clue that you need to do this in terms of y. Okay, so doing this in terms of y. We're going from -3 to 5 of my big function minus the little function, or the rightmost minus the leftmost. The rightmost is the blue function. The leftmost is the parabola. So remember that I need to get these as x equals. So getting the blue function as an x equals, I add the y over, we get 4 plus y. Getting the red function as an x equals. I'm going to kind of do some weird algebra here. It's not really weird. I just don't like. I'm solving for x. So I'm going to switch. I'm going to subtract the 7 and add the 2x over. And then I'm going to divide by 2. So then you have this function in here. Okay, so you have your big function minus your little function. Plug those in your calculator. Again, you could use x's in place of the y's. The calculator knows it's just calculating what that formula is. And we get 128 over 3. And you had to use y in this case because you couldn't solve this function for y. Because remember, if I was integrating with respect to x, you'd have to integrate and you'd have to get y equals. Because of that y squared, I would have to have two equations. It would turn into a really crazy integral. Okay? Okay, so that is your area between two curves. I hope you enjoyed that video, and I will see you all during class.